we have seen that for turbulent flow we can time average out the very rapid fluctuations resulting in the Reynolds averaged Navier-Stokes equations, which we can write in this form: dou u I bar by dou t plus dou by dou x j of ui bar uj bar equal to minus 1 by rho dou p bar by dou xi plus nu del square ui bar minus dou by dou xj of ui prime uj prime over bar. So when we compare this and also the time averaged continuity equation is dou by dou xk of uk bar. So when you look at these Reynolds averaged Navier-Stokes equations, we find that these are expressed in the form of the time average velocities and the time average pressure. Even the diffusion term here contains the time average velocity, so that if one were to neglect this, we would be expressing the momentum equation and the continuity equation in terms of time average quantities, and it's these time average quantities which enable us to make assumptions of steady state or one dimensionality or two dimensionality of the flow. Now the set of momentum equations is not complete without this extra term, and there are for each equation there are three such terms that are appearing in the momentum equations. There are no additional terms in the time averaged continuity equation. We have also made the point that these additional quantities involving the product of the fluctuating quantities cannot be neglected straight away, because for the case of steady one dimensional fully developed flow, the x momentum equation will reduce to 0, that is all the left hand side quantities become 0, equal to minus 1 by rho dou p bar by dou x, which is a constant when we have fully developed steady flow in one direction, plus nu dou square u bar by dou y square coming from this, the other quantities are 0, and the only non-zero quantity here will be dou by dou y of u prime v prime bar. And this is the case of fully developed flow through two infinitely long parallel plates which are separated by a constant distance under turbulent flow conditions. So the flow is taking place and you have a velocity profile like this. This is our y direction, this is our x direction. And if we were to neglect this term, which is the additional term which is coming here, then that means that this equation is very similar to the laminar flow part, laminar flow form of the equation, and we would be getting a profile which is parabolic with maximum velocity which is 1.5 times the mean velocity for the case of plane flow like this. But we know that under turbulent flow conditions through the same thing, if you expand this thing here and then draw it, you have the two plates separated by the distance h. Under laminar flow conditions we expect a velocity profile which is like this. Under turbulent flow conditions, experiments show that the velocity profile is more uniform, significantly more uniform than in laminar flow. And if we were to neglect this, and then if we were to solve only this, we would be getting only a laminar like velocity profile, not like a turbulent like velocity profile. Therefore this cannot be neglected, so this is not equal to 0 in turbulent flow, and therefore the extra terms that are coming here are not necessarily 0, and not only that, they have a tremendous influence on the turbulent transport of momentum in this particular case. If you were to take the energy equation and then time average it, you would find additional terms coming here, and those additional terms represent the tremendous influence of turbulent transport of energy and similarly turbulent transport of mass. So we cannot neglect these things, and we have to account for these so that we get turbulent flow like behavior of the flow parameters from our time averaged equations. And how can we write this? We need to know more about these fluctuations, and one of the early attempts at modeling this was to write this ui prime uj prime thing minus of this time average of this ui prime uj prime as being equivalent to a turbulent viscosity times mean shear based on the shear rate based on the mean velocity components, that is like this. And if we were to do this, then this particular term here would become minus dou by dou y of nu t dou u bar by dou y. Okay, so then under these conditions the flow the equation governing the velocity profile in this particular case can be written as minus 0 equal to pressure gradient is constant, so some given constant c plus dou by dou y of nu dou u bar by dou y, which is this one, plus okay, this is minus here, so this, because we are saying minus of ui prime uj prime equal to nu t times this minus is included, this becomes plus like this, so plus nu t dou u bar by dou y, or we can say, and we notice that u is a function only of y, we can replace the partial derivatives with the total derivative. We can say d by dy of nu plus nu t du bar by dy equal to constant. If you put minus here, then this becomes a constant. This constant is what is given for driving the flow, and this is what we get from the for example from the boundary conditions. Pressure at this end is this much, pressure at this end is this much, and therefore it is a pressure difference between the two which is driving the flow. So this is a given constant. Nu is a property of the fluid, so this is known, and in order to solve this we need to know nu t, that is the turbulent viscosity, turbulent kinematic viscosity, which is being used to model these additional terms that are representing the turbulent momentum flux. Now what can we say about this nu t? We know that turbulent momentum flux adds to the momentum flux coming from viscous forces, and therefore one can say that the overall turbulent transport in turbulent flow is greater than what we have, and we know that from increased friction factor. So one possibility is to say that nu t by nu is some constant C1, which may be, for example, 5 or 10 or 100, whatever it is, that it is the transport is increased by a multiplicative factor C1, and this C1 is what we want to do, what we want to input to this, so that the pressure gradient computed from this, or the volumetric flow rate for a given pressure gradient, matches with the experimental one. So one possibility is to prescribe a value, a constant value for the turbulent viscosity, such that the pressure drop versus volumetric flow rate, for example in flow through turbulent flow through a pipe, is honored. So essentially we are increasing the friction factor by a constant, by a certain multiplicative factor. That kind of thing is okay for the prediction of either the total flow rate or for the pressure gradient, given that the other component is given. But if you were to put this into this, then what this equation would become d by dy of this will become 1 plus C1, where C1 is nu by nu t, and we have nu here times du bar by dy equal to C, and all this is a constant, it is not a function of y here, so this will come out, and we have essentially another equation. This is nu prime d square u by dy square equal to C. Okay, so this equation gets transformed into an equation like this, which will give us a velocity profile which is exactly like a laminar velocity profile, although of a lesser magnitude because your nu prime is greater than nu. So for a given constant, a prescription of a constant multiplicative factor of turbulent viscosity will give us a lower flow rate, which we can match with the experimental volumetric flow rate by adjusting this constant, but the velocity profile that we are predicting will be laminar like and it will not be turbulent like. Therefore, prescribing a constant value, constant multiplicative value of the turbulent viscosity is not correct, but because it cannot give us a turbulent like velocity profile which is more uniform than the case of a laminar flow which is more peaking at the center. So the simplistic approach of ascribing a constant higher viscosity is not correct. So we have to make it, in order to go from this kind of profile to this kind of profile, we have to make nu t a function of y in this simple case. It has to be a function of y so that when this function of y acts on this profile, we will bring it back into this through this equation. Now what kind of functional variation can we ascribe to nu t? So for this we need to know this nu t is some kind of modeling of these terms here, these additional terms. We need to know more about these quantities. Instead of saying these quantities, let us from now on call these as turbulent stresses. These are also called as Reynolds stresses for obvious reasons. These arise from time averaging as per the Reynolds decomposition of the velocity into a mean velocity and a fluctuating velocity. So these turbulent stresses or Reynolds stresses are being represented through this turbulent viscosity and through this kind of thing. So we need to know more about these turbulent stresses. How can we know more about it? It is through experiments, because that empirical information of how to replace this as a function of the other variables can only come from empirical results, unless of course we take recourse to direct numerical simulation, and that is also being done to a great deal. So now what kind of what can we say about these turbulent stresses ui prime uj prime, which are 6 in number? We are looking at Cartesian coordinate system. So we have u prime v prime, u prime u prime, and of course u prime w prime, and then we have v prime w prime, v prime v prime, and w prime w prime. There are 6 Reynolds stresses or turbulent stresses, and we would like to know how each of these things varies in the general case with xyz for a steady flow, because these are time average quantities. These will be steady if the turbulent flow is steady in the sense of turbulent flow time averaged flow parameters are steady. So these are functions of xyz only if the flow is steady. So we will consider the steady case, and there is no reason to believe that all these are the same functions of xyz. So you have F1, F2, F3 like this, and these are what we need to know in order to replace these things coming in the momentum equations. Measurements tell us that the variation of these quantities even in very simple flows is very complicated. So the spatial variation of this, for example, if you take the simple case of flow between this kind of flow where you have fully developed steady flow between two parallel plates separated by distance, in which the flow is being driven by a constant pressure gradient, you can plot these turbulence stresses as a function of y, the distance from the wall, and typically the stresses will exhibit a variation like this. Most of these quantities, okay, the normal stress components, these three will exhibit a variation like this, and the variation, you can see that it is not a simple variation like linear or second order or exponential. So those kind of simple variations are not there because it is going through a peak and then it is coming down. And what is also very important is that if you were to look at the spread of this as compared to the channel width y by h, if you were to plot this in terms of y by h, then this peak occurs very close, it depends on Reynolds number, but it may be as low as 0.01. So it is within a small distance from the wall you may have a large peak of this, and then it behaves like this, and this is for one of these things, and another thing may be like this, and so this may be u prime square bar, so where u is in this direction, so this is x and this is y and this is z, and we are talking about a distance, a region which is very close to the wall here, because we are talking about y by h of the order of 0.01, 0.05 like this, and this is the variation not as simple as this. This may be the variation of w prime square, and this is of v prime square. So that means that all of them go through a peak, and then towards, as you go further and further away from the wall, they achieve an almost constant value. The magnitude of these things on a non-dimensional basis may be fairly small. This may be of the order of 10 to 15%. So if you were to say that, so what we are looking at is u prime RMS by u mean, where u mean is the average velocity through the duct, is of 10 to 15%, and this may be lower and this is even lower, and what we find is that here there is a strong effect of the wall in this region, but as you go further and further away from the wall itself does not play any, it makes the turbulence more more isotropic, in the sense that the three normal components have more or less the same magnitude, which may be the order of 0.02 or something like that. So the presence of a wall will fundamentally alter the way the individual stresses are changing, and we can see from here that the component of the variation normal to the wall, that is in the y direction, that is v prime square, is suppressed, and the component in the flow direction, that is u, is enhanced, and even w prime square is enhanced to some extent, but not as much as this. So you have a strong variation which is like this, and this is true even of flow in a boundary layer very close to the wall, and so on. So even for the simplest cases like one dimensional and steady flow, very close to the wall, we find a variation which is fairly complicated. And what we are interested in, what are coming into the momentum equations, are not the value of this u prime square and all these things itself, but it is the spatial gradient of this. So it is the dou u by dou x and dou y of these things, dou by dou x of this is coming in this, and other things will be coming. You have also this, and very close to the wall, all of them tend to 0 here, to go down to 0, and so in that sense they exhibit a complicated variation. The same plot is usually put in the form of not y by h, but in the form of y plus, which is defined as y u star by nu, where y is the normal distance from the wall and u star is known as the friction velocity, and this is essentially square root of f by 2, where f is the friction factor, such that f is equal to 16 by Reynolds number in the case of laminar flow. So, and I would refer you to standard books on fluid mechanics and turbulent flow to get this, and in such a case what we find is that the peaking of these stresses occurs for y plus of around 10 to 15, it happens, and then it goes on like this, and a typical maximum value of y plus, as you go from the bottom wall to the center, that depends on the value of the friction factor. So okay, u star by u mean is square root of f by 2. So as the Reynolds number increases, then u star increases, but typically this maximum value may be around 5000 or several thousands, maybe 2000 to 10,000 or even higher. So you have a very strong gradient of these stresses very close to the wall, and they exhibit highly nonlinear behavior very close to the wall, and that kind of highly nonlinear behavior in a small region is very difficult to capture in a CFD type of solution, because we normally use first order accurate or second order accurate methods, and the accuracy is very sensitive to the actual gradient of the quantity. So this is, but what we can draw from this is that these turbulence stresses are not 0, they exhibit a very complicated variation, and they do not exhibit a variation which is similar, although the for example the shear stresses components in this will be more linear, okay, not on the same scale, but it may be like this, very close to the wall. Of course this may be, this will again I have to come back to this. Okay, so you have a variation which is fairly complicated, and it cannot be predicted for the general case. For example, if you are looking at turbulent flow within this room, then a turbulence at this point is going to be influenced not only by distance from this wall, but also from this wall and also from the bottom, and also over the prevailing wind flow pattern in this. So it is a fairly complicated thing, and it is not possible to come up with simplistic expressions for the spatial variation of these turbulent flow quantities in the general case. So we have to come up with models which are not necessarily simple, because the underlying flow parameters do not exhibit a simple variation. And the other thing about turbulent flow, the nature of turbulent flow and the nature of turbulent fluctuations, is that we have said that f prime g prime, the correlation is 0 if f and g are independent. measurements show obviously that the normal stress components are not 0, but even the off normal stress components are not 0. So turbulent fluctuations are such that f prime, beta and g prime are not 0, and in a non-dimensional way they can be as much as even 0.3 like that. The cross correlation coefficient can be as high as 0.3 under certain cases, and so this means that there is some linkage between the fluctuation in u and the fluctuation in v, and similarly the fluctuation in v and fluctuation in w. So there is some sort of linkage, and this linkage has to be captured by us in order to make this model here. So what is this linkage? The linkage is such that a turbulent flow typically has a high degree of vorticity. So it is not irrotational, it is highly rotational, is a fluid mechanics way of describing this. So turbulent flow is highly rotational, and in a pictorial way one can imagine as the flow is going through this this duct here, it is not going in streamlines like this, in straight paths like this. The fluid is, it has these kind of eddy kind of structures, okay. So it has these small whirlpools spread throughout the flow domain, and a particular particle, instead of going straight through, it may be going like this and then may go off, and then it may go like this and then it may go off like this. So it is a fluid particle is not following a straight path in turbulent flow, and it is flowing a path which it is taking a path which is highly irregular, but which has a strong degree of rotationality, and this rotational element is not there all the time, and it is not always small. It may be part of a bigger rotation, it may be part of a smaller rotation, it may undergo the rotation only for a short time or for a long time. So typically what we express is that there are eddies or small whirlpools that a fluid particle encounters as it flows through in a turbulent flow, and these eddies type of objects that are present in turbulent flow are the cause and result and the sum and substance of this turbulent flow correlations, because these eddies are fluctuating eddies in the sense that they are formed and then they grow and then they decay. So they represent in a way these turbulent fluctuations, the characteristic of turbulent fluctuations, and for an eddy to form, a fluid particle here must go like this, and the fluid particle must here go like this, and a fluid particle must go like this here like this, so that you can have an eddy like structure. So that means that the v prime fluctuation here and the u prime fluctuation here must be correlated, so that as this moves, this moves. It is not exactly perfectly correlated, but on the whole one can see that there is, in order for eddies to be present, there has to be some sort of correlation between u prime and v prime at several points, at points within this, and also at the same point from time to time, and that is why this turbulent stresses, which are this f prime g prime over bar, are not equal to 0. So this is the fact that this is not 0 is for the substantiation of an eddy like structure in turbulent flow, and we must capture this, and eddy means that the fluid which is here is being mixed by convection with eddy from here, so with the fluid here. So this element will go quickly into this, and then it will mix and it will exchange the properties that it has, and if so the property exchange between a fluid particle at this location and at this location can now come about, because these two fluid particles are brought together by convection, by the macro movement of the fluid particle from here to here in the turbulent eddy. If this were not the case, as per molecular mechanism, if the property of the fluid element at this point has to be exchanged with the property of this fluid element here, it is only possible through viscosity, which means that this particle will exchange with this particle, and this particle will exchange with this particle, and this like this. So it goes through several particles and several interactions before it can effectively interact with this. So there are a lot of middlemen between this trader and this trader in exchanging goods, in trading goods. Whereas in turbulent flow, you are creating a railway path so that these people can travel up to this and then exchange goods. So the exchange and trading of the goods between this particle and this particle is faster because you have laid a railway track and it is easy for them to go. You do not have to go through lots of middlemen here who are exchanging between and then who are taking a long time and so on. So this is why that exchange of momentum and exchange of heat and all those things, the flux that is associated because of these differences is much faster in the case of turbulent flow, and that arises from the fact that this eddy type of structures are present. Another characteristic of turbulent flow is that not only are there eddies like this, but the eddies of different sizes are there, and it is this eddies of different sizes which actually gives rise to effective mixing. For example, if you are looking at point A here and point B at this point, these two have to be mixed, and we are talking about for example a chemical reaction which happens at molecular rates, molecular distances. Then this can mix, so all the fluid particles in this band along this sort of railway track will mix easily, okay, but there is no mixing of this fluid particle with this fluid particle, okay. So if you had only eddy of one size, then mixing would happen only up to a certain length scale, and beyond that it has to depend on molecular mixing arising out of molecular collisions. Whereas in turbulent flow you have eddies of this size, eddies of this size, eddies of smaller size, smaller size, smaller size, right down to very small lengths here, and the smallest length is determined effectively by the rate of dissipation of turbulent energy. It is determined by the action of viscosity on preventing those kind of very small fluctuations, and the largest size of the eddy is determined essentially by the physical dimension, the characteristic dimension of the flow domain. For example, the pipe diameter in the case of a circular pipe, or the distance between the plates in the case of flow between parallel plates, and typically the ball diameter in flow over a sphere. So these are the characteristic sizes, characteristic linear dimensions, and the largest eddy size is typically a fraction, a significant fraction, maybe 10%, 15% of the characteristic size of the overall domain, whereas the smallest eddy size is characteristic of the amount of dissipation of this kinetic energy associated with these fluctuations. That is, this plus this is a sort of kinetic energy of the turbulent fluctuations, and at what rate that is being dissipated will govern the smallest eddy size. Now what we want to say is that because you have an eddy of this size but also eddy of this size and this size like this, mixing will happen not only at this length scale but also at this length scale, also at this length scale, and also at this length scale. So that means that mixing can happen right down to very small scales, and that is when we have true mixing. Otherwise we will only see if you have mixing only because caused by one big eddy, then mixing will happen only in that band. There won't be mixing between this particle and this particle, okay. But if I have mixing not only like this but also like this, and like this I can see mixing happening over this, and these eddies are being convected by the flow. These are not stationary eddies. So this mixing that is happening here will transport further downstream, and then that also causes mixing. And not only that, the eddies do not of a particular size do not remain like that. They grow to a certain size and then they decay. Okay, so whether there are particular mechanisms by which eddies of certain size are created, and these eddies will slowly decay in size and then they go away. So you have a characteristic lifetime of an eddy and a characteristic size of an eddy, and these are random type of eddy kind of structures which are continuously being created and destroyed, and which are exchanging energy with each other. And so this kind of thing is expressed very nicely in a pictorial form, in the form of energy cascade, which is very characteristic of characteristic of turbulent flow. What we are plotting here is the energy, and this energy is turbulent kinetic energy. And what we mean by turbulent kinetic energy is this energy is proportional to half u prime square bar plus v prime square bar plus w prime square bar. Okay, so that is the kinetic energy associated with turbulent fluctuations. So one can say that, and what we have on this side is either the wave number which is proportional to 1 by lambda. So this is proportional to 1 by eddy size. These are very not mathematically rigorous definitions, and one can look up standard textbooks to get much better idea. But the essence of this is that, so when you have large value of k, that means that very small eddy size, and when k is very small, then you have large eddy size. So the largest eddy is fixed by the characteristic dimension of the domain, and if L is the characteristic length of the domain, then typically L by 6 is the largest eddy size, and you have the k minimum. This is fixed by the characteristic size of the domain, and then at the upper extreme you have k max, which is fixed by the rate at which this turbulent kinetic energy is being dissipated, and so that is usually given the symbol epsilon. So this is the rate of dissipation of turbulent kinetic energy. There are proper definitions for this, and we will get back to these things, but the higher the rate, the higher is the value of the k max, or the smaller is the eddy size that is possible. So in between this, the characteristic energy, it varies like this. So you have the turbulent energy is produced at by these large eddy sizes, by the large eddies, which are characteristic of the instability mechanisms that are happening in high shear regions. That is, high shear regions where you have large gradients of the mean velocity, which typically happens close to the wall. So that is why very close to the wall you have large values of this turbulent kinetic energy here. So of the order of the say point within 1% of the total characteristic length or duct size. So that is where most of the turbulent kinetic energy is produced, and then it is cascaded down in a characteristic variation. This is a log plot, log of E and log of K. it is cascaded, it is transferred from the large eddy size to the next size, next size, next size, next size, right down to the smallest eddy sizes like this. And when you come close to this K max, it is no longer possible to sustain these eddy sizes, and you have too much of viscous dissipation of this fluctuation, and beyond this you do not have any fluctuations or energy associated with this. So this is the energy cascade. So turbulence, the energy associated with this turbulent fluctuations is produced by eddies which are characteristic of the length size, which are of the order of the length size, characteristic length of the flow domain, through mechanisms, instabilities which are created very close to the walls. These are called ejections and sweeps and those kind of phenomena which are taking place in turbulent flow. Although this is an instability, there is also a self-regulating mechanism by which this instability does not go into uncontrollable system behavior. So it is produced here, and then it goes down and goes down to the smallest length here. So it is this presence of the eddies and the exchange of momentum between eddies of different sizes which is characteristic of the energy cascade, and one can therefore say that if one were to characterize turbulence, then one possibility is to look at this lowest eddy size that is possible to be that can survive in the turbulent flow against viscous dissipation, and on the other side of the spectrum you have the largest eddy size which is characteristic of this. So these are two reference points for which essentially determine the range of the eddy sizes and the characteristic features which cause the high turbulent transport of mass, momentum and energy in turbulent flow conditions. And typically for turbulent flow, for fully developed turbulent flow, for example Reynolds numbers of the order of 50,000 or higher, this variation here can be a few decades. So this can be something like an order of 10 to the power 3, and this can be 10 to the power 6 or even higher. So that means that K max by K min is of the order of 10 to the power 3, and similarly this may be of the order of 10 to the power 6 energy max and energy min associated, which essentially with measurable things is like this. And what is especially of importance is this range here. That means that fluctuations are possible of this kind of, we have said that this is the wavelength of the fluctuation, and which is also in a way loosely representative of the eddy size. So that means that you can have wavelength of fluctuation like this associated with lambda max or K min, and you also have fluctuations associated with the smallest things. Okay, so this is associated with lambda min. Now if you want to do a proper turbulent flow calculation which captures the full range of this turbulent fluctuations from the smallest size to the largest size, you must have a grid spacing which is much less than this lambda min. Okay, so your delta x must be much less than lambda min, and we know that from this lambda max by lambda min is of the order of 1000. So that means that the number of grid points to capture these variations maybe is of the order of 10,000. That is, so because if you say that delta x must be less than this, So you say that delta x is lambda min by 10, then the number of grid points that you have in one direction itself is 10 to the power 4 to capture the faithfully all these fluctuations. And we know that turbulent flow is 3-dimensional, so you have delta x, in the x direction you have 10 to the power 4 points, y direction 10 to the power 4 points, and z direction 10 to the power 4 points. So that is the number of points is humongous to capture highly turbulent flows, and so that is why these kind of computations are very, very difficult to be done in for highly turbulent flow calculations with very large Reynolds numbers. And the DNS that is attempted, the direct numerical simulation, where we solve the unsteady form of the 3-dimensional Navier-Stokes equations with small delta x and all these things, is typically carried out for Reynolds numbers of the order of 30,000. I think it has gone up to 30,000 or of this order, maybe 50,000 like that. Okay, so now we want to come back to prescription of how these things vary, the prescription of the functional variation of these things. So having seen the complexity of turbulent flow in the form, in the sense that there are highly spatial variations based on measurements and highly temporal variations in the form of eddies of vast range of sizes which are produced and being which are continuously getting bigger and smaller and exchanging with all kinds of things, therefore exhibiting highly temporal fluctuations. We can say that it is not possible to come up with a very exact description of these turbulence stresses. So people have tried to capture the essence of these things, of the nature of the turbulent flow and the mixing that it causes, through simplest prescriptions in the form of this effective viscosity, effective turbulent viscosity, which is causing these turbulence stresses. So in this particular case they are abandoning any attempt to make these fluctuations realistic in the sense of this turbulent flow characteristics that are present here, okay, in the form of eddies and all that. So that particular thing is essentially being subsumed in the definition of an equivalent turbulent viscosity, and a very simplistic picture for the justification of this turbulent viscosity is presented. The presence of these eddies of different kinds is equated to the presence of molecules as per the kinetic theory of gases, and so just as in gases the molecules interact, collide with each other and then therefore exchange momentum, it is also said that there is a possibility of similar kind of mechanism in the form of interaction of these eddies that gives rise to a viscosity. Okay, that kind of mechanism is what is thought for this turbulent viscosity. So this is where, for example, the simplest generic model for this has been proposed by Prandtl in 1925, and for the simple case of one-dimensional flow that we have here, he proposed what is known as a mixing length model. There are probably several interpretations to this, but the simplest way is to say that the fluctuations that are observed at a particular point is because fluid molecules from different parts are being brought to that particular point. So if you have a flow which is this is the channel dimension, you have a velocity profile. We know that very close to the wall it has to have low mean velocity, and as you move away from the fall you have higher and higher velocity. Now the nature of turbulent flow is such that there are eddies, because of which mixing of fluid elements from different heights takes place, and that is the reason why the fluid with a lower velocity here can come to a region of high velocity and exchange momentum. So if you are measuring the velocity at a particular point, sometimes you are measuring the velocity of a fluid element which is originally there, which has a mean momentum associated with that height. Sometimes you are measuring the velocity of fluid element which is brought from a different place, and then it's coming here, and if it is brought from a different place where the velocity is lower, you record a lower velocity, and if that fluid molecule is brought from a higher zone of higher mean velocity, then you record a higher velocity. So that means that the velocity fluctuations that you are recording at a particular point are because fluid elements with different velocities are being mixed by the turbulent motion, by the turbulent eddies that are present, and therefore you can say that if you were to take a velocity profile like this, we have the mean velocity as a function of y is plotted here, and this is the mean distance from the wall. At the wall you have 0 velocity, and as you move away from the wall the velocity is increasing like this. Let us say that you are making a velocity measurement at this particular y, let us say at y1. So the expected velocity is u1. So if you are now plotting as a function of time the measured velocity at u1, then it is going to show oscillations like this, and the mean velocity is this u1 bar y. So this is the expected velocity, but at different times you are measuring this velocity, this velocity, this velocity, this velocity like this, and the idea is that the velocity here is lower because the fluid element at that particular point has come from a lower height which had a lower velocity, and at this point it has got a higher velocity. You are measuring a high velocity because this particular fluid element has come from maybe a higher velocity region, and therefore you are measuring a higher velocity. So the fact that in turbulent flow fluid elements are enabled to move across different layers by these eddy structures can give rise to fluctuations. So you are saying that if a fluid element has come from a lower position here, then the velocity that you are instantaneously measuring is roughly the velocity at this position u2, and if it is coming from say y3 here, then the velocity that you are measuring is the mean velocity associated with that position, that is u3. So the fluctuation that you are measuring is the characteristic of the distance from which these fluid molecules are being brought here, and also the velocity difference, velocity defect that is there, or velocity extra velocity that is there for the fluid molecules at those distances. So you can say that if the fluid molecule is coming from y2, the instantaneous u prime that you are measuring here, this is u prime, is u2 minus u1 bar, and the velocity that you measured here is characteristic, the velocity fluctuation. So the velocity difference between the mean velocity that is expected here is u3 minus u1 bar. Okay, so the fact that there is the velocity fluctuation, deviation from the mean value, is because the velocity that you are measuring belongs to the velocity from a different place, and it is being brought here and getting mixed. So you can say that u prime is delta u. Okay, so delta u bar, where delta u bar is this one or this one, and it can be both positive and negative depending on whether it's coming from the bottom or the top. So essentially you are saying that on a time average basis you are measuring points from the coming from below or above. So and this is characteristic, this delta u bar can be given by a mean distance over which people the fluid elements are being brought forward. So it is a characteristic size of the eddy times the velocity gradient. So we can write this as L du bar by dy, where L is the mixing length. So he attributed the velocity fluctuation to a characteristic mixing length which represents the characteristic eddy size, a single eddy size from among which is representative of the net effect of this large range of eddy sizes, and to the velocity gradient that is present here. And of course we have u prime and also v prime, but we know from measurements this u prime and v prime are not very different. Okay, so u prime is of the same order as v prime, but we notice that when v prime is positive, that means that a fluid molecule has a vertical velocity, so that means it is coming from a lower height to this height, so that means u prime will be negative because your delta u is measured as negative. So when v prime is positive, u prime is negative, and v prime is negative, so it must be coming from above. When it comes here you record a positive delta u. Okay, so when v prime is negative, then u prime is positive. So that means that the correlation u prime v prime is going to be negative, roughly speaking. It is not an exact thing. So based on these things he said that minus u prime v prime is L du bar by dy, which is the velocity fluctuation u prime, and this is also of the same order. So again L du bar by dy. So this is L square du bar by dy whole square, and to make all possibilities we put this as L square du bar by dy, the modulus of this, and du bar by dy like this, so that if the velocity profile is not like this but in a different way, then even then this can work. So essentially you have an estimate for u prime v prime which is expressed in the form of a characteristic mixing length times the velocity gradient, and he suggested based on fitting and all these things, mixing length is proportional to k times distance from the wall, this proportionality constant being of the order of 0.4. So you have an overall expression for u prime v prime which is 0.4 times y whole square times du by dy modulus times du by dy. Okay, and this thing here is a characteristic turbulent viscosity. So you can say that minus u prime v prime is nu t times du bar by dy, where nu t is 0.4 y square times du by dy, the modulus of the velocity gradient. And you can see that that expression satisfies the requirement that nu t has to be a function of y. It is a function of y because it contains y itself, it contains y square, and it contains also the local velocity gradient. And also we can see now that we have an expression for nu t which does not require any more information. It is involved in y, which is an independent variable, and it involves gradient of the known velocity. So once you substitute this into this expression here, we have a single equation and a single unknown. We have closed the we have overcome the turbulence closure model in the simplest case. So this mixing length model is one model which is based on the, to some extent, on the physics of what happens in turbulent flow, which is that mixing which is caused by the fact that fluid molecules are enabled to move across different layers, and in the process they bring around an exchange momentum is encaptured in this. It has limitations and it has advantages which we will examine in the next lecture.